Hola, bienvenidos a la sesión de noviembre del Coloquio Iberoamericano de Álgebra y Teoría de Nudos. En esta sesión tenemos el gran placer de presentar al profesor Daciberg Lima Gonçalves de Brasil, que nos va a platicar sobre teoremas del tipo de Borsuk-Ulam para involuciones libres. Y su plática va a ser en inglés, entonces también voy a hacer la presentación en inglés. I thank you everybody to be here in the Ibero-American Colloquium of Algebra and Knot Theory. So this time we have the great pleasure and honor to present the Professor Daciberg Lima Gonçalves. He will talk us about Borsuk-Ulam type theorem for free involutions. So thanks, Professor Daciberg, and the time it's yours.
Okay, thank you. Thank you very much for the invitation, and it's good to be in touch with some people. And okay, let me share with you the. Please, at any time, just interrupt me. No problem. Please let me know if it's okay, and then you can see my handwrite notes.
Yes, now yes. We can see your handwriting.
Yes. Okay. First, the novelty of this talk is basically joint work with John Guaschi from Université de Caen, France, and Vinicius Laass from Federal University of Bahia. Bahia is a state of Brazil at the city of Salvador, which is the capital. Let me anticipate that, forgive me for the typos in these handwrite notes, because in fact, it's quite unpleasant how to fix it because of the computer treatment. But anyhow, there is a very famous statement which is known as Borsuk-Ulam theorem. And so let me revise recall what was this statement, and then we immediately see why it's so famous and continues to be a very alive theorem. So, in fact, in 1933, so Borsuk, which is a Polish mathematician, he published an article in Fundamenta Mathematica, and he answered a question which was asked by Ulam, and the question was posed in 1930. So despite the theorem carries the name Borsuk-Ulam, the proof Ulam was not involved, at least formally in the paper where this appears. And here's the statement. If you take a continuous map from Sn into Rn, then there is a point x such that f of x is equal to f of minus x. Well, this is certainly a nice and attractive result. So this shows that all function has some kind of, I don't know, symmetry, as long the space itself, which is Sn, has some symmetry. So what I call the space has a symmetry as the fact that you have the antipodal map, which is a continuous map, which has no fixed point, and such that the square is equal to 0. Okay. Now, when you look at this result, a very naive comment that you can make is this: any map from Sn into Rn cannot be injective. But in fact, the theorem tells that it's not injective in a very strong way. It's not injective, telling that there is a pair of points which are antipodal, which goes to the same. Now, look, if you know this theorem, once you replace your antipodal map for another free action, for another involution, means a map such that the square is equal to identity. I have not changed the map, just the fact that SCN support another involution, then the theorem should say that there is another pair of points besides the one which already exists, such that the 2 points collapse. But it's very easy that you can construct many different involutions on Sn. When I say many involutions, I mean say another map H without fixed points, such that the square is equal to the identity, and this map H is not the antipodal. You can just play. So if I also know that this kind of Borsuk-Ulam theorem holds for another involution, then the same map, automatically, a pair of points, which is tied with this new involution, comes out. So, in fact, the expectation is not that this is not injective, is that perhaps there are hundreds of pair of points which collapse. Not necessarily all are tied by the involution. So, the first thing that one may think about to generalize the Borsuk theorem is, okay, instead of the antipodal, put another involution on Sn. So now I'm going to start to see much more examples, and how far can I go with the examples by eventually replace Sn by something else, replace Rn for another space, and of course I should assume that the domain, it contains involution. But I mean, it could be artificial. I propose this very general thing without hope to have a technique to put my hands. So because of that, let me recall to you one of the proofs of the statement, which is here, proved by Borsuk. So we ask, are there other similar results? If A is the antipodal, means that we define a free action. This is just formula of Z2. So suppose I replace the antipodal map by a homeomorphism of Sn to Sn, which is fixed point free, which has the property that H square is equal to the identity. And then you make the same question. Does there exist, given F, there exists a point X such that F of X is equal to F of H of X? So if this answer is yes, you fix an F for every single H which satisfies this equation, you are going to get a pair of points, which is X comma H of X. Huh? All right, so okay, so now let me sketch the proof of the classical case. This is a second nice example in algebraic topology of something that you prove by contradiction. The other one is the Brouwer's theorem, fixed point. The fixed point theorem of the disk. So suppose that you have a map F from Sn which does not admit that's no good yet, which does not admit a point X such F of X is equal to F of minus X. If you use the addition of the target, because Rn, you can add and you can subtract, you construct a new map. This new map is called G prime, which is F of X minus F of minus X. So you can construct this map because you know how to subtract in Rn. And if by contradiction you said that X and minus X never goes to the same point, you have a map G prime which lies inside of Rn minus 0. Therefore, you can take the norm and you end up with a map G which goes from U domain, which is Sn, and you falls down in Sn minus 1. But this map that you have created has some symmetry. By symmetry, I mean, how do I relate G of X with G of minus X? So you just write what it is, and you easily see that G of minus X is equal to minus of G of X. So in a normal language, you are saying that the action of Z2 in the domain, it commutes with the action of Z2 in the counter domain, because everything here is explicit and so on. So if you have this so-called the equivariant map, the map which is commute with the action, you make the quotient. So you take the quotient of Sn by the action of Z2, the same in the target, And this gives you a map in two objects which have names. One is RPN and RPN minus 1 with the property, but now this is not an arbitrary map. So for example, the map constructed on this way cannot be the constant map. This map constructed in this way has a constraint. And the constraint is that the fundamental group here is an isomorphism. This came from the fact that this map here came from an equivariant map. But by classical cohomology theory, you cannot have a map from RPN to RPN minus 1, which induces an isomorphism on the fundamental group. So this, this use something, the cohomology ring structure of the projective plane, which is well known, with Z2 coefficients. So you got a contradiction here. So this map G bar cannot be constructed. Therefore, G prime cannot be constructed, and you prove the result. Okay. Now, this same proof, basically this same proof, you can show the similar result where in the domain, instead of to have the antipodal map, you have just a free involution. Yeah. And why the result goes through, we can construct G prime, there is no problem, because you still have maps into Rn. You can make the quotient, and now you have to use a little algebraic topology to show that if you have another quotient where the involution, even when it's not the antipodal map, but it's another free involution on N, you get a space which you have the same cohomology as the RPN, and then the result follows. So this is the most naive and first generalization of this. Okay, but using this approach, a lot could be done in terms of generalize. So a very natural and large set of triples for which we can ask the type of question proposed by Ulam, of course, are triples of the form X is a topological space, tau is a free involution on X, and Y is another topological space. And then you will make the question, which is the obvious one. You have a map from X to Y. You would like to know if there is a point such that X and tau of X goes to the same point. Okay, but you may ask, say, well, why are you saying that this large set, isn't this the whole thing? I mean, can you have something more general than that? Yes, but it's not going to be the subject of the talk. what you can replace is, instead of an involution, which is a free Z2 action, you could replace this by a free action of a finite group. I only say that this is a direction which has been explored, and anyhow, a lot has been done, but has another kind of difficulty to compare with the free involutions. So all the time we'll stay with Z2 action, and since this family is too large, I will begin with look this triple, but for the moment keeping the target to be Rn, because I can get some technique which is the very close of the classical case. So if you look at the subfamily of the triples where Y is Rn, I also going to make X to let X to be a manifold of dimension n. If we assume n greater or equal to 3, an approach similar to the classical proof can be successful use. So many manifolds of the dimension 3, we have answered if this Borsuk-Ulam question holds or not. And now we started to make the classification. Just, I'm going to give you a very simple example. If you take S3 with the antipodal map, of course we know that the answer for this Borsuk question, for the Ulam question, is yes. But if you take S1 cross S2, where you put the antipodal involution on S1, so this becomes a free involution here, and the answer is no. So for this space, you get a map from here into S3, which there is no pair of points which collapse. Okay, so many works has been done. Many people has been studying this question for this triple in this subfamily. So you have lots of results for 3 manifolds, but still there is a lot of them that we cannot answer yet. In particular, we have the hyperbolic, because as you see, you have to deal with the space, with the involutions, and you have to deal with the cohomology of that space. But I was a little bit modest, and let me present a result for the following set of triples, where the approach is still close to the classical. Then let X be a closed surface. And consider the collection of all 3 involutions that I call J of X on X. Now when I take all 3 involutions, I'm not going to tell the details, but we consider up to certain equivalence. Because when 2 involutions are equivalent, in some sense, the response for the Borsuk-Ulam is the same. So it turns out when you get a surface, when you get the set of all 3 involutions on this surface, this is a finite number. And the question is, consider all triples X tau sub I, R2, where tau sub I runs over the equivalent classes of involutions, and X runs over the closed surface. Does the Borsuk-Ulam property holds or not? So this is a classification. Here's the answer. Theorem 2.5. And you take a pair, blah, blah, blah. These are the hypotheses. This has the Borsuk-Ulam property, if and only if. So here's the answer. Let me tell you how you read this. When S is an orientable manifold surface, and the Euler characteristic is congruent to 2 mod 4, no matter what involution you put, the Borsuk theorem also holds. But when S is non-orientable, wherever this means, here's a way how to describe the involutions. For some involution is yes, and for other involution is no. And then they have different answer, depends on the Euler characteristic of the surface. Okay? All right. So up to this point, said, well, until now, this has nothing to do with braids and knots. They were just a thing. But how about if you take the contour domain Y and instead to have the Euclidean space, you put another topological space. What should you do? So suppose Y is no longer Rn. How to approach the problem? What should replace this map G prime, which was constructed this way as the difference between G prime of X equals to f of X minus f of tau of X? Well, this idea was in the air. What is this strategy? I'm going to construct a map which is called capital F, which goes now from X into the Cartesian product. This map F takes a point and encode the information of what F does in an orbit. So the first coordinate is f of X, and the second coordinate is f of tau of X. As in the classical case, suppose no for any point X, f of X is different from f of tau of X. If this happens, your capital map F has image in a subspace of the Cartesian product, namely the pairs y1, y sub 2, such that y1 is different from y2. This set has a name. It's the configuration space on 2 coordinates. So this map F, in fact, is a map from X into F2 of Y, which is the configuration space. More precise, the order configuration space on 2 coordinates. But This map F has a nice property. What is the difference between capital F of X and capital F of tau of X? When you do the calculation, you discover that what happens here is that the result is switch these two coordinates. Switch these two coordinates. That means the action of tau1, which is flip the coordinates. Well, so now you have created a map which is Z2 equivariant. And F, if you have a map which is Z2 equivariant, so that's the map that you have created, which is Z2 equivariant. When you use here the flip, so therefore you have a quotient map. And the quotient map goes into the quotient of F2 by Z2. This has a name, which is called the unordered, it's wrong, configuration space. Now, I want to also encode an information that this diagram came from a Z2 action. So believe me that this is a 2 covering, and this is classified by a map in RP infinite. This is a 2 cover, which is, yeah. So the end of this story is, if your map that you start with doesn't have the Borsuk-Ulam property, you are able to build this geometric diagram. I have not put the maps here, but that's the diagram. So we will obtain this geometric diagram. And if you want to study if this diagram exists, you may apply some geometric functor, algebraic functor. And for example, if this geometric diagram exists, you apply the fundamental group and you should get a algebraic diagram. So you must have an algebraic diagram. So what is this geometric algebraic diagram? Of course, here you have the pi1 of the space that you begin with. In the right-hand side, the pi1 is the braid groups on 2 strings. And here in the bottom, you have the induced map, where here is the fundamental group of the orbit space by the involution, wherever it is. And here is the full braid groups of Y. And naturally, because you took this quotient map, there is a natural map between pi1 of this onto Z2. And here's a classical thing in braids that P2 goes inside of B2, and you have the quotient map. So there is a strong constraint here. You should get homomorphism, which make this diagram commute. So if you have a surface here as a space, the existence of this diagram, algebraic diagram, is roughly speaking equivalent to the geometric diagram. If you have a surface this orbit space, you also know it's a surface. If your target is also a surface, you can profit that you know the presentations, these groups, these braid groups are known. And then you can study algebraically if such diagrams do exist. Okay, so the study of these algebraic diagrams has led to the classification of all triples, S1, tau, and S2, where S1 and S2 are two arbitrary closed surfaces with respect to the Borsuk-Ulam property. Okay, now I will give you the answer for all these triples where the approach using was this. This is a long statement, but I will make it shorter for you. Don't read all the corollary one. For us, the corollary one is just this. If X is a two-dimensional CW complex, particular, is a surface, and the target is S2, never you have the Borsuk-Ulam property. Never. Now, suppose the target is the projective space, RP2. There is only one case, only one situation where you get the Borsuk-Ulam property theorem holds, is if X is S2. Okay? And then the rest is a little bit more complicated to describe, but here it has a completely description of the rest of the remaining cases. Yeah. Okay. When you look this result, in fact, you say, oh, this is a very strong result. Well, this is a very strong result because the question was too weak. This is a very broad result because the question is too weak. So I would like to stress now a new version, not exactly a new version, is a problem which is the refinement of the Borsuk-Ulam property. Look, how do you prove that the Borsuk-Ulam property doesn't hold? You can have many, many maps from X to Y. You can have many, many homotopy classes of maps from X to Y. And if you just pick one which fails, if you pick just one and then you say, well, the theorem doesn't hold. So there is a more refined question is this, okay, doesn't hold, but tell me how many doesn't hold? This leads to the following question, formulation. Now I would like to introduce a more refined question which concerns the Borsuk-Ulam property as follows. Given X, tau, and Y, consider a homotopy class, bracket X, Y, set of homotopy classes of map. Then I'm going to define one particular homotopy class, if it's holds or not the Borsuk-Ulam property. The statement is clear. Yeah. So we say that the class has the Borsuk-Ulam property if X tau Y has the Borsuk-Ulam property for all maps which are inside of this class. Borsuk never would ask this question because the target was Rn, and in that context, we have only one homotopy class of map. Yeah? Just very briefly, if you want to see why is this question is natural, when you have the fixed point property, it's the same thing. One map has the fixed point property if every map has the fixed point property. But you can have a space, we have many homotopy classes of maps, and a whole bunch of them has the fixed point property and the others doesn't have. So, and very recently, we started to look at this question and to study this question, which now it's a little bit more involved because you somehow have to understand better how it looks like the set of homotopy classes. But anyhow, the good thing is that a similar approach like this one could be used. And here I will show you some results about this question. And the first result was, I do have 5 minutes. Okay, I have time. All right, so suppose, for example, that you look at maps from M to S1, S2. Okay? So perhaps this is a very most simple example because we easily classify those maps. For example, those maps are classified by the integer if M is orientable. Yeah. And yeah, if M is not orientable, is a little bit different. For example, if M is S2, which we are more used to it, so we will have, this index by Z is the degree of the map and so on. And you can ask for which degrees the Borsuk-Ulam property holds, for which classes it holds. So, for example, just read this for the sphere. You can see that one class has the Borsuk-Ulam property if and only if is not the homotopy class. Yeah. So for any degree different from 0, any degree different from 0, the Borsuk-Ulam property holds. On the other hand, if you take the class of the constant map, of course the constant map collapses many things, but there is a homotopy, a map homotopy to the constant map, which doesn't collapse no pair of points or no antipodal points. Yeah. So as you see, you cannot say that maps from M to S2, the Borsuk-Ulam property holds, because in one small place, which is the constant map, it doesn't hold. But you have a completely description which homotopy class of map is that. Okay, so if you continue this, theorem 13 and theorem 14 gave you the rest of the story for the other cases and so on. Yeah. So 2 more works were done after that, and I will just tell you what it is. Now you look at the maps from T to T. Maps from T to T are classified by matrix 2 by 2, because they are classified by what they do on the fundamental group. So the answer, in some sense, is going to be given in terms of a matrix 2 by 2. Happens that in the torus we have 2 involutions, and so we have to study this problem separately. One involution is when the quotient is the torus, and another involution is when the quotient is the Klein-Bottom. In the first case, the answer is more simple. The answer is somehow unexpected. It's that if beta is a homotopy class, then beta doesn't have the Borsuk-Ulam property. So it means you can always make a map that never collapses. But on the other hand, when the quotient is the Klein-Bottom, the involution that you take here is the Klein-Bottom, then we have a classification. And so we have this matrix, and then we tell you exactly what the matrix does. Yeah. Yeah. Okay. And now almost the last page. Now you move to maps from T2 to K2, and of course to state the result. This also was done. First, you have to recall, to revise how the maps from T2 to R2 are classified, and then you get here the description of which are the ones which satisfies one and the other one. Yeah. One word about this proof of this thing. This involves that algebraic diagram which consists in to solve some equations in a free group where this free group has an infinite number of generators. Well, to conclude, I put here a list of reference where most of the part of this talk, you will find in the references 9, 10, 11, 12, and 13. But this set of reference will give you an idea of many, many works which has been presented about Borsuk-Ulam in many directions. In particular, let me call your attention to the number 19, Steinlein, where this is a survey about the Borsuk property, Ulam theorems, which was published in 1985. And this survey contains 457 references. Okay, thank you very much for your attention. And yeah.
Thanks, Professor. It was a really interesting talk. I think there must be a lot of questions. If anybody has a question, please free to turn on your microphone or to do it by the chat, and I will transfer it to Professor Daciberg. So, well, well, if anybody has any question, I would ask, I would like to ask you, have you worked with different with different groups than set two? I mean,
Yes,
in the first part of the talk, you say that you can generalize these
right.
ideas, this Borsuk-Ulam for another finite groups, I suppose, or maybe even infinite groups. But
Yeah,
for finite groups, I think it's already quite interesting. Well,
yeah,
have you worked
yes,
a little about this with other groups?
yes. It's like this. Yeah. So it's like some people like Munchol and Isidoric from Poland, Munchol is from Denmark. They have been working in looking at finite cyclic groups.
Okay.
I think even in the spheres and so on. But myself, together with John and so on, and Vinicius, we have been working still with the surface, but we have already some results when the group is Sn.
Okay.
When the group is cyclic Zn.
Okay. Okay.
Okay? And it's also interesting because given any finite group, it acts freely in some surface.
Okay.
Even if you take this, in fact, the proof is like this. Even if you take the symmetric group,
Okay.
which is it's a group which contains a lot of finite subgroups.
Yes, of course.
There is a surface which this group acts, and so you get lots of example, and we have more or less reasonable results for the cyclic groups, but even in a very small case, low number n, we have even results for the symmetric group like S3. I know that it's too small,
Well.
but we in the surface, in the surface, but can be
You
done.
say that for certain surfaces, no, or for a certain surface.
Yeah, well, that's right. That's right. Because
You construct the surface from the group. I mean, you have the group, and then you say like, oh, if the group acts with these characteristics, the surface must have also these characteristics, and you ensemble it in the way that it works. I suppose. I don't know.
No, you're right. I mean, there are two ways to do. One way is like this.
Okay.
Somehow, it's known that certain action. That's, I mean, someone construct, some action, some symmetric action, which is in the literature. You know what's the action, using rotation and so on and so on. That's one way. Another way, which is more suitable to do your calculation, is like this. You take a group.
Okay.
You take a group which is pi1 of a surface. Suppose you perform a homomorphism from the pi1 of the surface into, let's say, the quaternion, Q8. So you are at the algebraic level. Suppose you built this map. As long as you built this map, this corresponds, the kernel is going to provide you with a cover, with a finite cover where the group Q8 acts. And so this way you have an example, let's say, just mentioned Q8, which acts in the surface, and you already get for free the quotient space, because you already start with your quotient space. So you have so it's like this. Either you construct action in this way using cover, or the action is given in somehow.
Yes. Okay. Okay. Now I see. Okay. Okay, let's give a chance to the audience. So another question. If not, I have another. Okay. Anybody has another question? Remember, you can do it by the chat also. Okay, well, I will I will use this opportunity to ask you another question. Just another one, I promise you. This other question is about in some part when you part to the fundamental groups, because you are taking the configuration spaces, no? I mean, if you don't have this fixed point, then you have differences and you have the configuration spaces, and then from there you take the pi one, no, the fundamental group, and so you have the braid groups, no. So I remember that you have some results concerning Borsuk-Ulam theorems or Borsuk-Ulam results problems with braid groups. So can you tell us a couple of words about this relation with braid groups or surfaces and these kind of spaces?
Yeah, it's like this. Look, can you see my notes?
Yes, we can.
Okay, it's okay. That's an important thing. When you have a map from X to Y, there is no problem to construct. I mean, you have a map from X to Y and you have involution. Of course, you can construct a map from X to the Cartesian product. Simply, you let, for every single X, you go to the pair f of X, comma, f of tau of X. This is no problem.
Yep. All right.
Now, suppose that you want to begin a proof. What to begin saying? Suppose that f, the Borsuk-Ulam property doesn't hold. This means that for every x, f of x is different from f of tau of x. Clear?
Yep.
So this means that the map that you construct in y cross y, in fact, is a map from X into the configuration space.
Yes.
This is the main connection. This is the main observation. From this point one, you start to see the consequence of the existence of this map. And once you have this map, and then perhaps because you recall the classical case, you ask, what does this map is equivariant? And turns out that a little calculation shows that it is. When you change x by tau of x, the target switch coordinates. So when you say that the map F does not satisfy the Borsuk-Ulam theorem, you create this geometric diagram. You create a map from X into the configuration space such that this map F factors through the quotient, and even more, the classification of this double cover makes this diagram commutative. Therefore, if you apply pi 1, you get a diagram involving the full braid, which has some, which imposes some restriction, this commutative diagram. So everything in some sense is concentrate here. So you can say that the non-existence, the non-validity of the Borsuk-Ulam theorem implies this diagram. So I can read for you, for example, the classical case. Suppose you want to prove the classical Borsuk-Ulam theorem, which is from Sn to Rn.
Mm-hmm.
See, you start with Sn, the quotient space is the projective space. Here, here you have B2 of Y.
Yeah.
Y is what? Y is, let me talk about R2. Y is R2, and so this is the arching braid groups.
Mm-hmm.
What is B2, the arching braid group? Is Z.
Z. Yes.
Z.
Yes. C.
So look at your diagram. In the left-hand side, you have Z2, Z, and Z2. How many maps exist from Z2 to Z?
One.
Trivial map.
Okay.
Therefore, this diagram doesn't exist.
Mm-hmm.
Since this diagram doesn't exist, so the Borsuk-Ulam holds, because this diagram is constructed. So, in this context, the proof of the Borsuk comes from the fact that you cannot have a commutative diagram with Z2 is Z2. And so,
okay. Okay.
So that's the connection, and that's the
Yes, but then you are only connected. You are only relating these Borsuk-Ulam problems with the two strands braids, no? In this context.
Which braids?
Two strand braids, as you have B2.
Yeah, no, yes, but I mean, if you have another group.
Yes, of course. If you have more,
you put more strings, and then you have to see how this group injects it's a kind of permutation groups.
Yes, of course. Okay.
And then you are going to replace the number 2 by some symmetric group where you group, I mean, there is a version of this for a finite group.
Okay.
There is a version of this diagram. It's a little bit more.
You will have n the order of the group or something like that.
Yeah, the order of the group is enough.
Okay.
The order of the group is enough because what you need is how to put the number of coordinates.
Yes, of course.
Which corresponds to the orbit, precisely. That's right. Yeah. But what happens is that it's much more complicated. The algebra. You see that's the difficult, because
Yes, you lose control over somewhere there.
But still can try. Eh? So,
okay, it's really nice. Okay, so if there is no other question, if somebody has any question, please feel free. If not, if there is not any other question, then we can stop. Okay.
Okay.
So I will stop the streaming. Just there we are. Okay.